Kodak Cannon Lab, Newton's third law. Here's my paper towel with the starting line on it. I'm going to put it on the floor. And I'm going to make sure that I've got lots of room. Now here is my Cannon. And I'm going to put an Alka-Seltzer tablet, or part of an Alka-Seltzer tablet, in here. Put the cap on. And then I'm going to put it together with the cannonball. This is the cannonball. So we have the cannon and the cannonball cap to cap. And what's going to happen is that pressure will build up inside of here. And eventually there'll be enough pressure so that the cap flies off. And what that will do is will apply a force to the cannonball, making the cannonball move one way. But then also, if the cannon pushes the cannonball, Newton's third law says that the cannonball pushes the cannon. So the cannon will go in the other direction. So what you'll see is on the paper towel right there, the cannon is going to go one way and the cannonball will go the other way. So now I'm going to get my Alka-Seltzer tablet. I'm going to put it in. And then I'll get the cap on as quickly as I can. Now hopefully this is not a dud. Sometimes you get a cannon that is a dud, but hopefully this one isn't. Sometimes it takes a while. And so we could be looking at this for not that long. Now you should notice that the cannon ball went way over. It pretty much hit the sink over there, or the cabinet that the sink is on. And then the cannon went backward the other direction and hit the wall. So basically I was in the middle of the room. That's where the starting line was. And both objects, both the cannon and the cannonball, went in opposite directions to the opposite wall. Now we're going to get data for this. So let me punch out of there. And let's go right to Newton's third law. Okay, so here's our data. Now, scrolling down, so I'm going to let you get to your data table. And here is what we have. We're going to only have one trial for each. And basically what this data is, it's the pooled data that has been compiled over about the last 10 years or so. So now right here, the distance traveled by the cannonball. Let me center this because I want it centered. On average, we get 5.5 for the distance traveled by the cannon for no sand in the cannonball. And then the cannonball travels about 5.7 meters on the average. Now when things are 1/3 full, the cannon again travels about 5.5 meters. The cannonball, now we're adding mass to the cannonball. So the cannonball is increasing mass, so it should be the same amount of force, but with more mass you know that there's not going to be as much acceleration because of that inverse relationship between force and between mass and acceleration. And so it's only 3.6. And now when it's 2/3 full, we get 5.5 meters again by the cannon. So the cannon travels the same distance every time. That kind of makes sense, doesn't it? Because it would be the same amount of force each time on the same amount of mass, because it's always 1/3 full and we add a 1/4 Alka-Seltzer tablet to it. And then we get 1.0 meters by the cannonball when it's 2/3 full of sand. So you can see that as you increase the mass on the cannonball, it travels less because of that inverse relationship between mass and acceleration. And then the cannon, same mass, same force each time, so you get the same acceleration, and therefore you get the same distance. So that is our data. And what you get to do right now is work on these analysis questions. This is when it refers to the data. This is what you refer to. And there you go.